Welcome back to another Forge College Explainer. So, have you ever actually stopped to wonder, how does the Ethereum virtual machine, organize its thoughts? Like, literally. Well, today, we're popping the hood, we're going to explore the hidden engineering behind Solidity data types, and trust me, it's pretty fascinating stuff.
Okay, let's dive right in. I want you to think back to your previous lesson, the capstone build, where you deployed your Hello World contract. Remember this innocent little line of code? It looks so simple, right? But uint public count is actually doing some major heavy lifting behind the scenes. With just this one line, you're making three massive decisions for the EVM: what type of data it is, exactly where it lives in storage, and what its starting default value should be. So today, we're going to unpack exactly how that whole shebang works. Here's our blueprint for today's explainer. We'll start with core primitives and defaults, introduce what I call the warehouse metaphor, tackle value versus reference types, look at some real-world examples, and then finish up with a quick recap.
All right, moving into section 1, core primitives and defaults. These are essentially the foundational building blocks of your smart contracts.
So think of the EVM as an incredibly strict warehouse manager. Seriously, it demands exact binary representations for absolutely everything. Whether you're using unsigned integers like a uint256, just a simple boolean, a standard 20-byte Ethereum address, or even dynamic types like strings, the compiler needs to know exactly how much space to clear out on the shelf for it. There's no guesswork allowed. And honestly, here is where things can get a little dangerous if you're not paying close attention. Solidity doesn't really have a null or undefined concept like, say, JavaScript does. Instead, it relies on these very sensible compiler defaults. Unassigned numbers, they default to 0. Booleans, false. Addresses default to the 0 address. Knowing these defaults is absolutely crucial, because think about it. If you don't realize an unassigned address is literally just a bunch of zeros, you might accidentally send funds into a digital black hole, and nobody wants that.
Okay, let's move on to section 2, the warehouse metaphor. This concept is a real game changer. It'll completely change how you visualize smart contracts. The absolutely crucial point here is understanding the storage slot. So imagine the EVM as a massive, highly regulated physical warehouse. A storage slot is basically just a permanent, heavy-duty 32-byte box sitting on a shelf. The Solidity compiler acts like an ultra-efficient packing machine. It actively tries to cram as many small items as it physically can into a single 32-byte box just to save you gas. And as we all know, gas translates directly to real money.
And this brilliantly illustrates the difference between where data actually lives. We just talked about storage, right? Those permanent 32-byte steel boxes bolted firmly to the warehouse floor. But when a function is executing, it needs a place to tinker. That's where memory comes in. Think of memory as a temporary wooden workbench. It is wiped completely clean the very second your function finishes running. You pull things from the permanent boxes onto the workbench, manipulate them safely, and then put them back.
Now let's step into section 3, value versus reference. This is probably the single most critical behavioral distinction in all of Solidity data types.
First up, we have value types. I want you to think of these like physical items, say a shiny gold coin or a physical calculator. Because they contain their own independent data, when you assign a value type to a new variable, you are literally manufacturing a brand new replica and placing it into a completely different warehouse box. That means if you take a hammer and smash the replica, the original is perfectly fine. They are totally separate. Now, reference types, they behave completely differently. Arrays, structs, mappings, these are massive objects. The EVM doesn't want to haul all that heavy data around. So a reference type variable is really just a paperslip holding directions to the real boxes. If you copy a reference variable, you aren't copying the boxes at all. You're just handing your friend a duplicate paperslip. You both now have directions pointing to the exact same set of boxes. Building on that idea, static types are fixed size, like our uint256. They fit neatly right into those standard boxes. But dynamic types, like a resizing array or a super long string, they can grow. They just don't fit in a standard box. So they get stored off-site in a different part of the warehouse, and the main slot just holds that paperslip, a pointer telling the EVM where to go find that sprawling mess of data.
All right, section 4, real-world examples. Let's see how this literal warehouse logic dictates actual code execution.
Okay, let's look at example A. Here we have a simple value type assignment. Variable A equals 5. Then we say variable B equals A. Simple enough, right? Well, if we trace the execution here, step 1 puts the number 5 into box A.
Step 2 creates a brand new replica of that 5 and puts it into box B. So in step 3, if we decide to mutate B to 10, what actually happens to A? Absolutely nothing. Box A still holds the number 5. It's independent, safe, and entirely isolated. Now let's contrast that with example B, where we use a dynamic array which, remember, is a reference type. We have a storage array called R. Then we declare a new reference pointing to it saying uint array storage ref equals R. Let's walk through these execution steps. Step 1, we push the number 1 into R. Step 2, we say ref equals R. But remember our metaphor? We did not copy the array, we copied the paperclip with the directions. So for step 3, when we say ref.push of 2, we follow the paperclip to the main warehouse location and add a 2. Meaning, we just modified the exact same underlying on-chain storage that R looks at. They are entirely linked.
Let's check out our final kind of tricky scenario here. Example C, dealing with mappings. A mapping is essentially a giant dictionary or a ledger, mapping address to uint public balances. So when we ask for the balance of a specific address, let's call it who, we expect an answer.
But here is the catch. Because Solidity doesn't have a null value, if a key exists, you get the assigned value, say 500 tokens. Great. But what if the key has literally never been written? Well, it doesn't crash. It just returns the default value for a uint, which is 0. And returning a 0 could mean that address just spent all their money and has an empty wallet, or it could mean they have literally never interacted with your contract at all. It's super ambiguous, so you have to design your logic carefully around this.
And that brings us to Section 5, Recap. Let's wrap up our engineering schematic here.
Let's solidify this new mental model. Moving forward, always consciously choose. Are you copying actual warehouse boxes or just handing out duplicate paper slips? Remember that static types pack neatly into 32-byte slots to save gas, while dynamic types use off-slot storage and pointers. And finally, always explicitly check your default returns. Don't let a phantom 0 trick your contract logic.
Now that you are fully equipped with the knowledge of how data physically lives inside the EVM, you are perfectly prepared for our next lesson in the track, Integer Types and Number Basics. We're going to apply this exact slot packing knowledge to bit widths, sign semantics, and explore the occasionally terrifying world of integer underflows.
But before we go, I want to leave you with a bit of a provocative thought about optimization. Think about this. If memory is just a temporary wooden workbench, and storage involves heavy-duty steel boxes permanently bolted to the warehouse floor, how might gas costs drastically differ if you have to make 50 changes to a variable? Would you do it on the workbench or out in the warehouse aisles? Think about the physical effort involved. It's a massive difference. And that wraps up today's session. Thank you so much for joining this Forge College Explainer. I really hope this visual breakdown has made the mechanics of Solidity finally click for you. To keep building on this foundation and to learn so much more about Web3, be sure to visit forge.college. Keep exploring, and I'll see you in the next one.